uh, in some time, let's add the people first. So meanwhile,
Okay.
share your starting screen.
Yeah, sure. I share my screen. Yeah.
Yeah.
So, can you see it?
It seems blank to me.
Yeah. I mean, that is.
Okay, then
Mhm.
yeah, that's fine. So we will wait for some participants more, and
Yeah,
we'll
sure.
start. Okay.
Okay. Okay. Hello.
Yes, Souvik, you're audible.
Yeah, it's okay. Mm.
Hello.
Yes.
Yeah. So everybody, welcome to the DCMP General Club. So today's talk will be given by Souvik Sasmal. He has done his bachelor's from BSc from Vidyasagar University and his master's from IIT Madras, after which he joined TIFR under Professor Thamizabe, where he works in Crystal Growth Lab. So without further ado, let's start the presentation. And also, if you have any questions, you can message in the chat or raise your hand. I will unmute you and you can ask the questions. So, Shovikda.
Yes.
Yeah. So
Yeah.
we can start.
Thank you, Rishabh, for the nice introduction. Okay, hello everyone. Actually, in our lab, we grow different type of crystal. We do grow by for research purpose, not for industrial interest. So here we grow different type of crystal that may be very useful for our looking for different electrical properties or thermodynamical properties. So Today I will give a very short introductory talk on the different type of crystal growth and few transport result on flux grown calcium Ag bismuth and calcium copper Sb single crystal. So coming back to the yeah, okay, why it is not moving? Yeah, so the crystal growth involves a variety of research field ranging from the surface physics to crystallography, material science, and industrial sector. So it has been extensively studied for maybe more than 100 years. People are trying to looking for different technique to grow different material which may not be easy to grow. So always there is a more modern technique these days. But why do we grow this crystal? Means what are the importance of the doing such experiments? So it has industrial interest. In semiconductor industry, people use silicon. Um, so these are very important material in technology purpose. So in semiconductor industry, it has a large extensive interest, along with high temperature superconductor material or detector physics or 2D material or thin film in electronic devices, and also photonics and laser science, which is mostly applicable in medical science or biological purpose. So coming back to the different type of crystal growth, I here shortly describe three techniques where in our lab also we employ to grow different type of crystal. First is Czochralski method. So the silicon crystal has been grown by this technique, basically, and other is gallium nitride or cobalt silicon. There are many materials. So here you can see this is a large silicon single crystal. It may be something like 100 centimeter, even larger than that. Also, this is it is in some industrial sector. So these are very important crystal which people used in semiconductor industry. And the other techniques are flux growth. So the crystal you can see here, those are grown in our lab. So this is calcium based crystal. So here you grow you grow the crystal from supersaturated solution. So I'll come to that point also one by one. And coming to the second, then that is chemical vapor transport. So here you take material and you have some transport reagent, and by small molecular transport you can get big size crystal. So mm, we have also employed these techniques to grow different 2D material, mostly like a TMD material or Zeta T5 or layer structure material. So I come one by one. So so in Czochralski, it has a very interesting discovery, and it has been discovered by Dr. Czochralski. So he was writing, the story is like that. So he was writing with his ink pen, and to write ink pen, you need to dip that pen to ink. But by mistakenly, he dipped his pen to molten tin. Tin has melting point something like 230 or 250. So while he dipping and taking out, he found that something like some strange happened. So some string kind of things or some needle shape kind of things he found. So he was so surprised about that. Then he discovered that the grown, that needle shape kind of thing was tin crystal, and it has been experimentally verified, or I can see it has been explored for a long time how the crystal grows actually for this process. So coming back to the point how we grow, first I go to looking at the solid liquid phase diagram. So you can see this is cobalt and this is silicon. This is the solid liquid phase diagram of the cobalt silicon phase. So so if you look at this point only, so you can see if you take 50% cobalt and 50% silicon, you got this dome and the corresponding this dome line, and it has melting point of something like 1500 almost. So when you have this kind of solid liquid dome phase, then you expect that this composition might be same at that molten state. Meaning, if you melt, if you take 1:1 ratio of cobalt and silicon, and you make polycrystal by heating, then you get 1:1 phase, not the other phase. If you go to some other areas, if you take a random composition somewhere, let's say somewhere this area, something like 85 or 15, then if you melt it, you may not be having the same composition throughout the material. So for this Czochralski method, it is important to have this dome line that basically indicates whether you have the uniform phase or not. So let's say you have taken 1:1 ratio and you melt it. You, by melting, you get polycrystalline material and it has 1:1 composition. So we got some polycrystal. Then what we do? We pull the, we cut the polycrystal and we take a small seed. Here you can see this is the seed. So we take seed and then we tie the with the pulling rod. Then we slowly pull the pulling rod from the melt. So while pulling very slowly with 10 am per hour, we get a large size crystal. This is basically the Czochralski pulling. So by pulling it, we got something like 7 to 8 centimeter crystal, and for that case, you know, it is important to undisturb the system. So slow pulling is important for that case. So you can see this is grown cobalt silicon crystal, and it has been verified by Lawe and other experiments. So I will not go very deep, but this is what is the picture is. So coming back to this other technique, that is chemical vapor transport. So for that case, we take polycrystalline powder. So then we sealed in a quartz ampule. You can see this is the quartz glass ampule, and we put iodine as a vapor transport agent. So you have polycrystal and you have some transport agent. Don't think about that much. You have something like some transport agent and some polycrystal, and you sealed inside a quartz tube. Then you put this ampule in a furnace, one side induced by some hot zone and other side is cold zone. So here you can see the basically hot zone indicated by fire, and that side you have that polycrystalline powder. And while you put one side in hot zone and other side in cold zone, you have transport of this powder element by the transport agent. So by slow transport, you know, by one that molecular layer will be introduced, and by this way you can get a single crystal. I show you a real image where you see the here it has been kept, the polycrystalline powder has been kept here, and this dull color comes from the iodine. So you know, it has been kept for something like 1 month, and by putting this hot zone and cold zone with some temperature gradient 100, we got something like this. So these are the grown single crystal that has been found on the cold region. So here I can show one small piece that indicates that the grown material is like very shiny, and it has its own structure. So this is basically CVT grown Jeda T5. Next, I come to the flux growth technique. So for that case, what we take some composition ratio of material, and we take flux as a huge amount. So here you can see my uh, aim was to grow calcium Ag bismuth. So I took calcium as a 1, Ag 2, and bismuth some large amount 20. So I took 1:2:20. And I took inside a alumina crucible, and then I sealed in a quartz ampule, and then we keep in furnace for heating. So the temperature profile for that one was something like this. So we heat up to something like 1050. Then by slow cooling, we came to 420 degrees Celsius, where we extract the single crystal from the flux. So this is the real image. You can see this is the alumina crucible, which has been sealed inside the quartz ampule, and this is the grown crystal. So in the whole process, the flux has been removed, because my aim was to grow calcium Ag bismuth. So it has some large amount of bismuth also. When we keep that amount of like 1:2 and 20 ratio, that means you have large amount of flux. So in that case, while you heating the material, you have bismuth as a molten state as well as calcium and Ag. So that molten state basically becomes supersaturated solution when you heat up to high temperature. So in the supersaturated state, basically calcium Ag bismuth will form, and they start growing inside the ampule. And the other flux will be on the molten state while coming down to low temperature. So here bismuth as acting as a like flux material. The salt can be grown by dissolving in water. So you can think about that bismuth working as a water here. But water we can extract very easily, but the metal at very high temperature, it is difficult to extract. For that case, we do centrifuging. By centrifugal force, we take out that excess bismuth. So good. So we got different type of crystal from different techniques. But coming to the point, as I described, that I will discuss a few transport properties from few flux growth technique that employed in our lab. So here is calcium Ag bismuth. It has hexagonal in structure, and it is known that it has the band structure shows it has some Dirac point along the high symmetry line. Okay, fine. So, but the most interesting thing is the magnetotransport. So you can see this is basically the magnetoresistance versus field. So the magnetoresistance basically shows a cusp-like behavior in low field, and it has almost linear type of behavior at high magnetic field. And this low field cusp-like behavior is known as a phenomena like weak antilocalization. I will come to the point what is basically that phenomena meaning. So this is the magnetoconductivity plot. It shows the same kind of behavior, but in magnetoconductance form. In ballistic case, the electrons can move very freely without, the lowest scattering. And while in diffusive region, the electron gets scattered through the scattering center. But when you have the quantum diffusive region, meaning you have something like scattering center, and electron gets scattered, and you are able to see some kind of quantum phenomena that's evolved in terms of whether it is weak destructive interference or constructive interference. That all the phenomena depends on whether the phase coherence length is larger than the whether your phase coherence length is larger or smaller than the mean free path. I briefly describe one by one. So as I explained that in quantum diffusive region, electron can interfere. So you have the scattering center here. The scattering center are indicated by the red dots, and you have electron path. If your weakly disordered system is somehow capable to do some kind of scattering that may able to show the interference effect, and that happens when you have the phase coherence length basically larger than the mean free path. So you have for phase coherence length larger than the mean free path. Then, so even after scattering, you have basically the no change in the phase. And when you have interfere with the other electron path which has some phase difference angle, then it basically can interfere, because after and before scattering also this electron path has the constant phase. So then your system is able to show some kind of interference effect, and this interference effect can be explained by this HLN model, that is Hikami-Larkin-Nakagawa model. Don't think about that. You just come to very simple ideas. So it has basically a quantum interference term, and other is classical conductivity term. Look at the quantum interference term. It has the function of L phi, that is phase coherence length, and some alpha term, that is alpha parameter, that indicates that number of conduction channel in the system. If you have monolayer, then you expect that alpha to be half or 1 if you consider some kind of degeneration or the contributing up and when it's 2 layer. But our system is not monolayer. Our system it has multi-layer transport. So when you have this multi-layer parallel transport, then you expect this large alpha value has to be very large. So you have parallel conduction channel, and each channel contributes to this magnetoconductance data, and you get a large value of alpha. And from the magnetoconductance data, you can find that alpha and L phi value. You can see the magnetoconductance data is very much well fitted by this HLN model. That describes basically what is the phase coherence length for your case and how the alpha value is in your system. Okay, so we got phase coherence length. We have idea about the alpha value also, but we want to see how this alpha and phase value changes with the temperature. This has been measured in different direction, and you can see as you increase the temperature, the L phi value, basically the phase coherence length, decreases due to the basically the phononic contribution come to the picture. And as the phononic contribution comes, I can show you, as the phononic contribution comes, see that this quantum interference effect will die out, and classical conductivity plays important role than quantum interference. So so that it decreases rapidly, and at very high temperature it must be killed. Okay, so and I so this is the angular magnetoconductance data. I come to how it has, I mean, how this gives the idea about the weak antilocalization in our system. So you can see we have measured magnetoconductance at different angle. At low magnetic field, it basically merges. But you can see this is this is the b sin theta value for different sample and different direction, and you see at low magnetic field it almost merges. That basically signifies whether your system is the 2D parallel conduction channel or not. I briefly describe that what does it basically meaning of this having 2D parallel conduction channel. So if you have this is like your sample. To find the origin of this weak antilocalization, what we do, we rotate the sample at different angle and we look at how the magnetoconductivity behaves. So for that case, we rotate the sample and you measure the magnetoconductance at different angle, and you look at when you plot the magnetoconductance as a function of normal component of the magnetic field, then you see whether in low field the all data are merges or not. If it is merges, that means your then basically your magnetoconductivity data depends on only the normal component, that means the perpendicular direction of the field. So that indicates whether your system has 2D behavior or not. So coming back to the second case, the calcium copper Sp. Here we did not take, we have some interesting composition of the material to grow 1:1:1. See, I have taken 1:4.5:7.5 ratio of calcium copper Sb respectively. Here, somehow copper and Sb, it has some kind of molten composition working as a flux. We are growing. My aim was to grow 1:1:1 but we have taken 1:4:5:7.5 ratio. So crystal growth is not easy job to find out. If you take some other composition, you may not get the crystal. So you have to make a good trial to get proper composition. So for that case, we employed some different temperature profile. So here you can see we have ramp up to temperature 1550 with at the temperature rate 30 degrees Celsius per hour, and we cool down to 627 where we centrifuge the material. And by centrifuging, we extract a single crystal. This is single crystal grown in our lab also. And we verified with Laue diffraction experiment where it shows the whether your pattern are matching with the theoretical simulated model. So it has been verified that our grown crystal is the single crystal. Coming back to the point, in the closed pack cubic structure, electron can move in all three possible directions almost with equal probability. But this calcium copper Sp has some kind of layered structure. Here basically copper Sp layered, here basically two copper Sp layered are sandwiched with the calcium layer. It has some kind of 2D metallic 2D metallic sheet kind of things. So what would be the transport for this kind of system? So in generally for this kind of system where this metallic layer are present, that are likely to participate in the transport. Basically something like look like quasi 2D nature. You can see this is the calcium copper ruby crystal. So as I explained, in the AB plane you have this metallic layer and the insulating calcium layer, and along C direction you we measured the resistivity along C direction and along A direction. You see along A direction the resistivity is quite low, but along C direction, as it has the insulating layer along C axis, then the resistivity increases for that case. So this anisotropy is very clear from the resistivity data. If you look at the magnetoresistance data, so for first case we measured the electric resistivity along A direction and field along B direction, meaning you have current along this direction and field along C direction, this direction, and you got the magnetic resistance like this. See, again, it has some kind of cusp-like behavior at low magnetic field. And if you look at very high magnetic field, you have some kind of linear type of behavior, and it has some kind of oscillatory behavior that I will not go very deeply. Something corresponding to SDH oscillation, but don't think about that. So now you can look at here. It has this cusp-like behavior, which already I explained for the earlier system that is known to be weak antilocalization. The same way, we also checked whether this weak antilocalization properties are originate from this 2D kind of nature or not. So we rotate our sample, and again we look at for different angle. You can see when we plotted the magnetoconductance, normalized magnetoconductance with the function of normal component of the magnetic field, you have almost merging for different angle. That indicates basically again the 2D conduction channel in the system. So coming back to the quick summary, all the two results that I have shown, those are grown by Flux method, and it has hexagonal it has hexagonal structure, and cusp-like negative magnetoconductivity presence in the system that basically suggests weak antilocalization behavior, and angular magnetoconductivity shows that parallel conduction channels presence in the system. And this weak antilocalization happen when your phase coherence length is larger than the mean free path, and that already verified with other experiment, but that I did not explain here. For simplicity, I did not put for those data. And the last one, that is phase coherence length decreases with the increasing temperature, as I showed earlier, where the phase coherence length die out with increasing temperature. And thank you. Thank you very much. Hello.
Hello. Yeah.
Hello. Yes.
Sure, thanks for the talk.
Yeah, I have given. Yes.
Okay, so we have a question from Joydeep.
Oh, okay. What?
Yeah, he is asking. Let me unmute him.
Yes, Jaideep.
Yeah, Joydeep, can you ask a question?
Yeah, so I had only small question. So
Yeah.
I was asking what is the key condition for getting single crystal? So for example, when water naturally flows to ice cube, is that ice cube a single crystal?
No. That too just indicate I come to point. Yeah, this one, right?
No, it's just a picture, but in general, I was asking.
Yeah. So to grow single crystal, very important to undisturb the system, and you allow the basically molecules sit in a proper manner. For in a very naturally also crystal grows, so it takes something like thousands of years to grow that single crystal. You allowed basically the molecule to sit properly one by one, and you undisturb the whole system. These are the two conditions very important. And to grow the single crystal, the material has to be in molten form or very slow cooling also important. Hello, you got my answer? So you can see for here, for this case, so you have some kind of polycrystalline melt, but then what you do, we dip the seed crystal inside it, and you then slowly pull. So while slowly pulling, basically you allow to material to attach with the seed one by one, basically atom layer. So while this atomic layer sits on the seeds one by one, then you get this single crystal. If you pull very fast, then you won't expect that to be single crystal. See, for to grow something like 7 to 8 centimeters, we took 8 hours to grow this single crystal. So this is very important to allow the system by slow cooling process. Yes, and you cannot grow anything anything as a single crystal, because you have to have that proper phase diagram, whether that things exist. I mean, whether that can be grown by this process or not. Yeah, anything cannot be grown by any method. Okay, Jaideep. Hello.
Okay, if anybody has any question, they can ask in the chat. I can unmute them, or they can raise a hand.
Yes, Rishabh, can I just ask a few
Yeah.
questions? I think I've got a couple of questions.
Yes. Yes. Yes.
Yes, so hi Souvik. So it was a really nice
Yes.
talk. The questions I have may appear somewhat trivial. So can you just go to the Magneto resistance curves that you got?
Yeah, sure.
Yeah.
Yes.
Yes. So
This one on, yeah.
yes, this
Yeah.
one, this one. So my first question pertains to this particular curves that you have on the left. So my question is, when you do the magnetotransport measurements, how do you ensure that you don't have any remnant magnetic field in your system?
This is, first of all, this is a non-magnetic system, and remnant magnetic field may come from the instrument itself.
Right.
For so how do I confirm that there is no
Yes,
remnant
yes, yes,
magnetic?
yes. I mean, for example, in superconductors, what we do is that we do
Yeah.
when in terms of the mutual inductance method, when we do the two-coil measurements, we check for where the mutual inductance value is the lowest. When we do a magnetic field
Yeah.
sweep and measure the mutual inductance real part value. So wherever the mutual inductance value hits the lowest point, we get to know that that is the actual zero magnetic field. So in your case,
Yeah.
what parameter do you observe to confirm that? Is there anything of that sort, or you do follow a different methodology?
No, for our case, we may have some small remnants magnetic field, but that doesn't affect here because this is completely non-magnetic. And to check, we generally, before starting measurement, we oscillate the magnetic field to kill any kind of remnants, but still you may have some kind of remnants field also. But that may be very low, but for that case we did not measure here the remanence field. Yeah, but
Okay, so I mean, so you're saying that I mean, if there is still a repetent field, I mean, can you like estimate the order? Like, I mean, can you just give an offhand figure?
yeah,
Like, is it
that may be 50 or 50 or 40 or state
40 or so? So it basically
yeah.
doesn't affect your measurement.
No, that doesn't
Since
affect
your
my
magnetic fields are
measurement,
extremely
but
high.
it present in the system. Yes.
Okay, okay.
Present in the
Okay, and another question I would like to ask, that is regarding the resistivity measurement that you do along the different principal axes.
Yes.
So
Yes.
in that regard, I would like to ask, so when you do a measurement along a particular axis, so it's not like that, like the current is flowing only through that axis. There is at least a little bit of mixing from the other
Yeah,
axis as
that
well.
will be there. That will be there.
Yes,
That we cannot avoid.
yes, so my question is like, how do you minimize the effect from the other like crystallographic directions, or like, is there any like, yeah,
Yeah, to orient the crystal, first of all, we do lave, and by lave we can orient the sample first. So
okay,
first I orient the sample along crystallographic C direction
right,
and crystallographic A direction. Then we
okay,
cut the sample. But even though you cut the sample, it is not like that. It will be exactly parallel to A axis. That won't be there. Some
Right.
disturbance will be there, right? So and other thing is along C axis, but that disturbance will not because as it is not much I mean tilting, then you may expect something like parallel in the bulk case, like
Okay.
yeah.
So
If you cut the material like this, but yes, as you said that if there are little misaligned involves in the system or not, yes, it may be, yeah, it
but
may be.
that small misalignment doesn't play a major role in your
That will
samples
not
because
affect, no,
most
no,
of
no,
your
no, no,
samples are bulk
because
samples, right?
yes, these are bulk system, yes.
And also, like, what typically what magnitude of current do you send in to measure these resistivity, to do these resistivity
Almost,
measurements?
yeah, approximately 10 milliampere.
10 milliamps.
Yeah, 10
Okay.
milliampere. It has a low resistance or very low
Okay.
resistance.
Okay.
So we can send something like 10 milliampere also.
Mhm. Okay. Okay. Thank you, Souvik.
Thank you.
Yes.
Okay, Divya Das, can you unmute yourself and ask the question?
Yeah. So
Yes.
one of my question is from the last slide. Go to the next slide. Yeah. So you no. Yeah. So you say that as these cards are coincide,
Yeah, merging to each other.
it means that it proves that this is 2D.
2D in nature. Yes.
How that is?
How do? So to check that case, what we do, we rotate the sample. See here, you see the angle theta. That is basically the angle between current and magnetic field. So when you rotate the material and you are measuring the magnetoconductance, and the thing is you plot as a b sine theta, meaning you always looking along direction perpendicular to the surface, right? So let's say, uh, so I show you. So here the angle between current and magnetic field is almost 90 degree. So my b sine theta is b. Now if I rotate something like, let's say, now the angle between current and magnetic field is something like 60 degree. Let's just assume. So the normal component of the magnetic field will be this along this direction, right? And that will be some b 60 degree. See, if this b60 value matches with other angular normal component of the magnetic field, meaning you are looking along the field only perpendicular to the surface. So only thing is matter to you the perpendicular of the magnetic field at any angle. So you rotate the sample and you look at the magnetoconductance, and you have only the effect due to the normal component of the magnetic field. Meaning, so when does it can happen? It can happen only you have something like 2D surface and you rotate the sample, and at different angle the b sine theta value, when your magnetoconductance as a function of b sine theta merges with each other, that only tells you the 2D nature. If you have some kind of bulk 3D transport, then by rotating your sample, that the magnetoconductance effect may be coming from the different all b direction. But when your only perpendicular components affect the magnetoconductance data or resistivity data, that basically indicates that your transport is 2D like, because this is simple mathematics. So I rotate my sample and it has effect only due to perpendicular component. You understood, Dibba?
To some extent, but still not clear. Anyway, I will talk with you.
Yeah, I can.
Yeah.
So okay.
So I didn't notice that it is b sine theta plotted.
Yeah, it has b sine theta because we are always looking for the normal component of the magnetic field.
Okay.
Okay.
And another thing is in the flask method you describe this. Finally, you remove the flask by centrifugal. So is when it is in molten state, you
yeah, at the molten state itself, by centrifuge, you keep the ampule inside, and it has been heated, and it has been go through different temperature profile, and at high temperature you take out the ampule,
Okay.
and at that temperature you centrifuge. By centrifugal force, the flux will come out and it will accumulate somewhere here.
So at that temperature, flux will be liquid, but your sample will be
Liquid,
solid.
yes. As the crystal has been formed inside, that will be in solid form and inside the ampule.
Oh.
But the flux is in molten state, which can be, extract by centrifugal force.
I see. And another thing in the CVD process,
Yes.
how you so ensure that there is no mixing of iodine with the sample?
Yes.
Transfer.
Sometimes so here this case we take Jedar and TE as a polycrystalline powder. Sometimes iodine can also react, but for this case we explored that iodine doesn't affect this Jedar or TE. So that case we can use iodine as a transport agent. Somehow, so for specifically that case it doesn't affect. So if you have some other material that may, if you think that may affect that may affect iodine in your sample, then you cannot use iodine as a transport agent.
Different material.
Yeah. For that case,
and also
sulfur
process,
or yes.
I see. Yeah. Also in this process, how you ensure that the layered by growing will happen, not a like island kind of growing.
Yeah, see, I'm not telling that only that layer will grow. I mean, by layer growing, you may see the island type also. Okay, so from the hot zone, the element will transport to cold zone.
Mm-hmm.
So it will accumulate here, and you may see some needle-like shape also, or some kind of island like also. That may also you get.
Okay.
It is not only that you can see only needle shape. So that is also possible. But the important thing is this: most of the like TMD material or that MOAC2 or WAC2, all those materials, layered materials, can be grown in this CVT process, because those are very easy to grow by this process. This is why people are more extensively use this process to grow those kind of layered sample. This is why I said yes. There are many materials can be grown all three processes, CVT, flux, growth, and Bridgman, Czochralski also, that I have shown all three process, and I tried all three process to grow one type of crystal. That is also possible.
Okay.
Yeah.
Another question Shonot was also asking, there's the
Yes.
ratio you are using. Is there any guidelines to choose the art that you?
Yes. It doesn't have very hard guideline, but you have available phase diagram of two element. You do not have available of phase diagram for three element. You can see this is phase diagram for two element, cobalt and silicon, and you have liquidous and solid line. From there you can choose that which composition are preferable to grow. That is fine. But as I described, for let's say for cobalt, silicon, or calcium Ag bismuth, you have three elements. You do not know which composition will work. To grow this calcium Ag bismuth, I have tried 6 times to grow. At the 6th time, I got using this ratio, taking the ratio. So if you take the bismuth as something like 10 instead of 20, you may not get. I'm sure you may not get, because in the low flux cases, it may be that flux are attaching with the material, or somehow it the flux takes out the silver also along with it. So it is important to get proper ratio unless you do proper trial. So it is important to give a proper trial to get this one. So earlier I used when I was trying for the first time or second time, that time I took calcium as a 1, silver as a 1, and bismuth as a 10. That time I did not get, what we get, I got something like polycrystalline ingot inside, and it did not have any kind of silver there. Then I realized that something I need to increase silver to forcefully go inside and obtain the my desired crystal. So you have to play. You do not know exactly which ratio will work out. So yeah, but when you become expertise and you have a good idea when you have the calcium element or bismuth element or antimony element, what should be the ratio of for that case, then that will be easier. So yeah, so after getting this formula, I got different calcium based single crystal. So I later on then I quickly got a few crystals. So this is like a trial method.
I have one small question here.
Yes.
Yeah, so to begin with, how do you choose like which element to use as a flux? Like why not flux? Choose
Yeah,
flux.
so flux is known to have very low melting point. So so for that case, which are the low melting suitable low melting point are available, we always look at those. So for that case, we use bismuth as a flux. When you flux, you have to be very careful whether the flux itself can act as, sit inside your material. So you can use flux from the external element also. Let's say I'm just randomly telling, if you want to grow some A, B, C element, you can use D as a flux element. That's also possible. People also do like this, but you have to make sure that D will not react with A, B, or C. So best way to choose flux is first you choose any of your material as a flux. So here bismuth has quite low melting point, so forcefully I took bismuth as a flux.
Okay.
Okay.
And another small question. So when you separate this flux by centrifuging,
Centrifugal. Yeah.
So is there any residues of the flux that remains on the crystal? And how do you
Yeah. Okay. So while centrifuging, the ideal case, you expect that all flux come out and accumulate here, right? But sometimes even you centrifuge, some amount of flux may be sticking inside, and it may be sticking with your crystal also. Right. So to remove that one, some solvent can be also used to remove that flux, or after polishing also it can be removed. So you have, let's say, some kind of, say you have this kind of crystal and you have something small tiny flux attaching with your single crystal. So you cut the top layer or you polish the top layer so that you can remove the all flux with your crystal. Yes.
Okay. Yeah, thanks.
Yeah, thank you.
Okay, I guess Surajit has a question. Surajit, can you unmute yourself?
Yes, Surajit.
Weak localization curve.
Yes.
The two curve you are showing your measurement data.
Yes. Okay.
Go to the next, I guess. No, the two sample curve. No, go. I think forward.
Okay.
Yeah, this one. Okay,
yes.
if you see the calcium, silver, bismuth, that the bottom one, there is, I can see a crossover. What is the physical significance of that crossover? Higher magnetic field region from low temperature to the high temperature.
It has not very much significant ideas. No, this crossover doesn't have any kind of meaning here. This is just.
So why it is crossover then?
So I tell you. So see, these lines are at low temperature. So in low temperature cases, you have that quantum interference term is dominating. But at high temperature, you have quantum, low impact of quantum interference and large impact of classical terms. So classical terms basically gives you the linear term, and so at low
Quadratic
temperature,
term, B square, I guess.
quadratic B square term. So due to this term, basically at high field, it increases very rapidly.
1 minute. What control the beta parameter?
Yeah, this is the beta parameter.
That is depend upon your beta value also. It might be if my beta value is low, my classical contribution also low. Even if I don't go to the too much high temperature, I can see there is also it possible to cut, because even it's like if I go to like let's say the 30 Kelvin above, I don't think so it is too much dominating.
Yeah, too much dominating. Here the magnetic resistance goes down.
Okay, so so it might be little bit of critical at this point. So let's There is another question I have, that is that you estimated from your feet that the phase coherence length.
Yes.
So did you estimate it from any other to verify this? Because fitting parameter can give any value, but how you cross check that this is correct value? Let's say in the order of it is correct ballpark or not.
Here you have three parameters basically, L phi and this alpha or A value. So and beta value, and it has very
it is the three parameter fitting. So my question is that fitting parameter can be fitted many ways. So is it give you the correct ballpark value? How you know that?
Whether we did any other experiment to verify or not?
No. So you estimated mean free path also somehow.
Yeah. We estimated mean free path from SDH oscillation, and we observed that.
So in the single crystal, mean free path also large. How much mean free path it is?
Yeah, for I can tell you. Okay, just 1 minute. For this case, this is I did. We got SDH oscillation for this system, and from there we calculated the mean free path. That is something like 60. 60 nanometer.
60 or 70 nanometer.
Yeah. And for that case, no. The mean free path is something like 50, and the phase coherence length is 70. For that case.
So they are very close. You are saying.
Yeah, close meaning that 20 is difference.
So that's why I'm saying that how you are sure that this is that in the other estimated it is coming in the correct ballpark or not? Because one way you can do also means this is maybe the little bit of rough, but still it can give you, as far as my understanding also. But I don't know too much details about how this thing is going on in the current state. So like see the magnetic field is not too large, this cups like feature. So I can still think about that the conduction still happening is near to my Fermi level. So from that electron density through the Hall measurement, one can estimate your Kf for using free electron theory, and you can still have the de Broglie wavelength, which is basically this phase coherence length or the quantum length scale are you talking about? Is it right?
Yeah. So that gives you the mean free path.
No, that's give you lambda, this de Broglie wavelength. That is what is the phase coherence length in the quantum mechanical length scale are you talking about?
Yeah, but
now second thing that is that, so as you also estimated the thermal length scale.
That is basically
thermal decoherence length scale, where you are destroying this. Since you are studying your studies like a large temperature length scale. So I am I am expecting that somewhere it might be affecting or not. Thermal length scale, like let's say I have a KVT temperature, so then I have also length scale. I can also calculate the lambda also. So how much is comparable?
Okay.
Okay, we can talk about later. Souvik.
Now, why I'm telling it is, why we expect that is phase coherence length is correct. You can see if you apply current along C direction, you don't see weak antilocalization.
No, that
because
is not my point. My point is, see, where you expect it or not, that is different. I am saying that it is not respect to magnetic field. I am saying that if I have a weak antilocalization, I have estimated that phase coherence length value from the fitting. Okay, that is my
yeah,
second question was. But how I am sure that this is my phase coherence length come to the correct ballpark or not, since it is very close to my mean free path. Generally, generally if they are very close, now I have to be sure. My second question is that since you are studying as a function of temperature, if you go to that again two curve, where is the two sample you are showing? The two sample you are showing. No, next I guess. Next. Yeah. So you see, this cups like feature is not vanishing. Like see, I don't know that color which is because these numbers I cannot recognize, but let's forget about it. But I am asking that where these thermal length scale are playing a role, because let's say you have a KBT temperature, there also you can estimate the thermal length scale, that above which this thermal fluctuation destroy your quantum phase.
yes, yes.
So what is that length scale?
This
That
is
is
what.
I am asking you, because
See,
here you are talking about the length scale as a competition.
Yeah. So we can see this weak antilocalization up to almost 200 Kelvin.
So
And
this is you get
above
from
that,
the fitting, now Souvik, this red points
yeah,
are okay.
yeah, this is from the fitting, but this nature is present up to something like 200.
Okay.
Then it almost linear.
So
that means it get destroyed.
Okay. 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 Thank you. It was a nice talk.
Okay.
Okay, so anybody else have any question? Raise your hand, or you can type in chat. I can unmute you. Okay, so it seems there are no more questions. Thanks for the wonderful talk, Ragda.
Okay, thank you very much.
Yeah, so I guess we can conclude the chat, conclude the talk here. Thank you.
Thank you.